Mr. Hassan's Maths channel. I'm now answering question number 4 from the October-November 2018 Pure Mathematics P2 paper from Cambridge 9709. Now this is a question which is very much related to the P3 exam. As we know, P2 and P3 in Cambridge are basically, P2 is completely contained within P3, except for one topic which is not in P3, which is called the trapezium rule. All the other topics in P2 are actually part of the P3 syllabus. So sometimes I take questions from a P2 paper to give practice to my students on a certain topic. So here we have a question which is in the worksheet about iteration. My other topic worksheet about iteration because of part 3 of the question, but parts 1 and 2 are basically related to the factor theorem and algebraic long division, and I'm going to save those in a separate video from part 3 because this is like I'm going to save them according to their topics as well as the questions. So anyway, so let's start with part 1. So first of all, we're told here that we have a curve. The diagram shows a curve with the equation y equals x to the power 4 plus 2x cubed plus 2x squared minus 12x minus 32. It's this quartic curve. And it says the curve crosses the x-axis at the points with coordinates alpha 0 and beta 0. So alpha looks like the negative part of the x and beta on the positive. Okay, then we're told that use the factor theorem to show that x plus 2 is a factor of this equation. Okay, so of this expression. So to use the factor theorem, okay, basically what we do is we find the value of x that makes the bracket that we have to show is a factor 0. So x plus 2 equals 0, so x equals negative 2. And then we call the function, so I'm going to call this f of x, equals x to the power 4 plus 2x cubed plus 2x squared minus 12x minus 32, and then I'm going to replace the x with negative 2. We'll see what we get. Get negative 2 to the power 4 plus 2 to the power of negative 2 cubed plus 2 times negative 2 squared minus 12 times negative 2 minus 32, which gives us the negative 2 all to the power 4, so it's an even power, so that's going to become positive 16. And you're going to have plus 2 times, this is going to be negative 2 cubed, which is negative 8, plus 2 times negative 2 to the power of 2, which is an even power, so it's going to become positive 4. And minus 12 times minus 2 is plus 24. And we've got minus 32. So let's see what that gives us. We have 16 minus 16, plus 8 plus 24 minus 32. As you can see, that gives us 0. That gives us 32 minus 32 gives us 0. So we can see that as f minus 2 is equal to 0, therefore x plus 2 is a factor. Okay, so when we put minus 2, we replace the x with minus 2 in the function, we ended up with 0, which shows that x plus 2 is a factor. So something like this must be written down, okay, as a statement. So there's the answer to part 1, which is pretty simple. Now part 2 tells us start. Okay, so part 2 tells us about, or tells us to show that beta, which is the other root, we found this is basically minus 2. Okay, when x plus 2 is a factor, that means when you put this equal to 0, x equals 2, negative 2 is going to be one of the roots of this equation. Okay, equals 0. We're now told that beta, which is the other root, satisfies an equation of the form x equals a cube root of p plus qx, and state the values of p and q. So here we have the equation that we were given. Okay, we call this f of x. Okay, and we know that x plus 2 is a factor. So if we want to find beta, beta is the other factor. Okay, beta is the other factor. So it tells us to show that beta satisfies an equation of this form. So what we have to do is we have to take this and we have to use algebraic long division. So we'll have x plus 2 into this and we're going to find what's left, and then eventually we'll show this. So let's see what happens when we put x plus 2 and use algebraic long division. Okay, so x into x to the power 4 goes x cubed times. This is my column for x cubed. X cubed times x gives me x to the power 4, and x cubed times 2 gives me plus 2x cubed. This looks a bit weird here, but just carry on as we normally do. Don't worry, it looks a bit strange, but that's fine. Of course, these two will cancel out. Now this minus this, it doesn't normally come out like this, but now we've got 0x cubed. I'm going to carry on the same way as I normally do. I'm going to bring down the next term. That's 2x squared. Then I'm going to say 0x cubed into x goes 0 times. You can say 0x squared times, you could even say. All right? You don't really have to write this down, but I'm just trying to do it so that we don't lose track of our normal procedure. So 0x cubed times x is 0x cubed. And 0x cubed times 2 is, again 0x cubed, x squared. 0x squared times 2 is 0x squared. Now we're going to subtract these two. So this gives you 0. This, of course, gives you 2x squared. We're going to bring the next term down, which is negative 12x. Same procedure again. 2x squared into x goes 2 times. We're going to have plus 2x times, 2x times. 2x times x is 2x squared. And 2x times plus 2 is plus 4x. And we're going to subtract again. Of course, this part gives us 0. You've got negative 12x minus 4x, which is negative 16x. Bring down the next term, negative 32. X into negative 16x goes negative 16 times. Negative 16 times x plus 2 is negative 16x. And minus 32, which is exactly how it should be. We should get 0 here because we know this is a factor. When you divide, you should have a remainder of 0. So we can say that the other factor is, you can say therefore now that x to the power 4 plus 2x cubed plus 2x squared minus 12x minus 32 equals 0. Okay, can be factorized into x plus 2 times x cubed plus 2x minus 16. So we know that one of the factors is minus 2, which we already worked out. This is your alpha. And the other factor can be found by solving this equation where x cubed plus 2x minus 16 equals 0. Now to solve this, or to express this in the form that they asked, we can see what we need to do is we need to add 16 to both sides and take away 2x from both sides. You have 16 minus 2x. So x is going to be the cube root of 16 minus 2x. That is one form that we can express this solution, okay, for beta as, okay. So and state the values of p and q. So p is the constant, so p equals 16, and q is the coefficient of x inside this, so q is negative 2. All right, so that solves this equation here. Now for part 3, I was going to put it in on a separate video, but I'm not going to now because it's like a very short part. But I will save this video in both playlists for the factor theorem and also in iteration. I'll save it in both playlists so that you can have a look at that. So now we're told to use an iterative formula based on the equation in part 2, which is this equation that we found here, to find the value of beta correct to 4 significant figures, give the result of each iteration to 6 significant figures. So our iterative formula will be, if you want to find the next value of x, you're going to put it into this iterative formula where you have the cube root of p, which was 16, and it was minus 2, was it? Minus 2 times x to the power of 1. So we have to start off with a value of x which is close to our root. Now we can see from the original question that beta is around here. We know this is minus 2, and it doesn't look too much further away than the minus 2 and the positive 2. So I'm going to start off my x1 value as 2 because it's close. It looks like it's quite close to the root. So I'm going to start off with 2. It really doesn't matter. If you start off with 1, it probably also should give you the same value. But you start off with a point which is close to the root. Okay, so what I'm going to do now is I'm going to replace the x here with 2. Right, so I'm going to say that x2 is going to be the cube root of, not the 16th root. The cube root of 16 minus 2 times 2. Okay, so what I'm going to do with my calculator, I'm going to take my calculator and I'm going to press 2. I'm going to press equals. That is now the answer in my calculator. I'm going to set this up so that I don't have to keep on messing about with my calculator all the time, I'll say the cube root of, which is this button here. Okay, and I've got 16 minus 2 times answer, right? So right now this is going to be 16 minus 2 times 2, okay, which is 16 minus 4 will be cube root of, 16 minus 12 minus 4, which would be 12, so it'll be the cube root of 12 right now. Okay, so I'm just going to press equals and I'll write down my answer. And that gives me 2 point, and they want us to write the result of each iteration to 6 significant figures. So we have 1, 2, 3, 4, 5, 6. So 2.28942. 28942. That's 1, 2, 3, 4, 5. So there's going to be 43 at the end. 2.28943. 2.28943. 2.28943. That's 6 significant figures. All right, for each iteration, and the final answer to 4 significant figures. So now I'm going to find what x3 is, and I'm going to take the same procedure. I'm just going to basically replace this now with 2.28943. So I'll replace this with this value. Now we don't have to type that in because now this is now the new answer in my system, in the calculator. So when I press equals now, it's going to put this number in that place, exactly what we want to do. So I'll press equals again. It gives me 2.25201. 2.25201, and then I'm going to press it again. So I'm going to press 2.25692, 2.25692, 2.25692. 1, 2, 3, 4, 5, 6. Again, that's the 4th iteration. Okay, I'm going to keep going until I got the until these numbers settle down. So 2.25627, 2.25627, 2.25627. So it looks like it's starting to settle down. Let's just do it a couple of more times. Okay, let's see what happens. We press equals again. Press equals 2.25635, 2.25636 actually, 2.25636. Okay, so it looks like it's going to be 2.256. Let's do it a couple of more times. 2.25635, 2.25635, 25635. It looks like it's settled down now. Okay, I think that's enough. Let's just press equals again. You can see it's settling down to that. So 2.2563. 2.256 to 4 decimal places, or to 4 significant figures. That's enough for us to get to the answer. So we can say, therefore, our beta is equal to 2.256 to 4 significant figures as they ask us to give. All right. So there's the answer to part 3. And if you want to justify that this is the solution correct to 4 significant figures, what we can do is we can take the upper bound and lower bound of this value, which is 2.2565, and the lower bound will be 2.25655. That'll be the lower bound. Okay, that's the upper bound and lower bound of this number here. So basically, this number here is 2.256, you can say 0, and this is 2.2565, and this is 2.2555. Okay, 2.255. Right now, basically, what's going to happen is if the beta root lies somewhere, anywhere between this value and this value, it will round to this number. Okay, to 4 significant figures. So if the root goes through the x-axis anywhere between these values here, when you round it will become this. So basically, if you were to put inside the original equation 2.2555 and 2.2565 into the original equation, which is this one over here, then you would find that the sign should change between them. Okay, that before the first one should be negative and the second one should be positive because it goes up in that area, as we can see from the graph. Okay, it goes up. So before that root is going to be negative, after the root is going to be positive. And if that is the root correct to 4 decimal places, or 4 significant figures, that's exactly what's going to happen. So let's see what happens just to show. Oops, just to show this. So we're going to have, I'm going to put 2.255, 2.2555. Okay, and I'm going to call this as A. And I'm going to put 2.2565, and I'm going to store this as B. Okay, so I'm going to take A. So I'm going to put shift. Okay, so this is going to be A to the power 4. Okay, plus 2 times, 2 times A cubed. Okay, 2 times A cubed plus 2 times A squared plus 2 times A squared minus 12 times A minus 32, and that gives us negative, negative 0.062, negative 0.062 ... And when we replace the A with a B, okay, so I'm going to take the A and replace it with a B. So shift, store, and B. I'll replace this with B as well. So shift, store, and B. Replace this with a B as well. Shift, store, and B. Okay, that will give us the upper bound now. Shift, store, and B. Now that should give us a positive value, which it does, which is 0.0112. 0.0112. So we can see that as between x equals 2.2555 and x equals 2.2565, there is a change of sign. There is a change of sign, and our function, which we call f of x, is continuous. Therefore, the root beta is equal to 2.256 to 4 significant figures. Okay, because we chose the upper and lower bounds. Now you don't have to write this last part. If you've done all of this, that's fine. Okay, but if you didn't do all of this, for example, and you just like kept pressing equals until it settled down, then you could prove that this is the root by using this justification method. So once you've pressed equals enough times for you to realize what the root is, you could justify that this is the root, okay, by using this method of taking the upper and lower bound of the root to 4 significant figures, and then showing that the upper and lower bound give us one answer, which is the answers have changed signs. If there's a change in sign, that means the root must be between those two values, which means any number that comes between these two values, if you round it to 4 significant figures, it's going to end up being 2.256. That shows that the root is 2.256 to 4 significant figures. All right. So, in this case, of course, the question seems to be like you keep giving the iterations, but the mark schemes do mention this justification method. It's more kind of common in the Edexcel syllabus, where they'll say justify that this is your root to so many significant figures. It's something within the syllabus, so we should know it. So that's why I try to explain it as well as the other method in my answers. So that completes this question from the 2018 October-November paper 2, variant 1. And this, as I said, is part of my P3 syllabus collection. We teach P3, not P2, because our students, P2 is really only for those who stop at AS. So P3 contains all of P2 and also the extra stuff from P3 as well. Other questions from this particular paper you'll find in the playlist over here. Other questions from my P3 collection, I'm going to collect this all together under one playlist for all the questions dealing with the factor theorem and the remainder theorem and algebraic long division together in one playlist will be placed over here. There will be a playlist over here dealing with iteration, okay, which we just did in part 3 of the question. And you can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.